Hello and welcome to what is the last video on an absolutely mammoth chapter for Year 13's Edexcel A-level course on integration. So it's 11.12 where we're going to have a look at essentially how an integral is defined in terms of limit notation. And the absolute limit using this tends to the exact area under a curve. Now this particular bit of the course is almost like an add-on. It almost feels like an afterthought, and it's not a huge part of the syllabus. In fact, it's very, very small indeed. And when you see the questions, you should hopefully realise that they're actually very simple in terms of the concept as it's presented. The proof of a concept is entirely different altogether. So I'm going to explain integration from first principles, as it were, in a different video. But all will be revealed. Until that point, I've given you two warm-up questions to try. Only two, because it illustrates the difficulty of these questions when we get to this stage of the course. Doing 4 warm-up questions might take quite a while at times. So the first one is essentially trig identities and a trig equation, and the second one gets you into implicit differentiation. So maybe just pick one of the two, ideally try both, press pause and try them now, then press play to see the solutions to your answers, and hopefully yours should match mine more or less, or exactly. Okay, assuming you've had a go at the warm-up questions, let's have a look at the solutions together. So question 1, use the double angle formulae and the identity cos A plus B is equivalent to cos A cos B minus sin A sin B to obtain an expression for cosine 3x in terms of powers of cos x only. So for part A, what I'm going to suggest we do is just do this very, very carefully, step by step. So first of all, let's write down what cos 3x will be. And it does say explicitly to use this formula. So I'm going to split the cos 3x into a cos of 2x plus x. Then just using what I've got here, so in our case A is 2x and B is a single x, this is going to become cosine 2x cosine single x minus sine of 2x and sine of x. Now, using the double angle formulae, we can replace cos 2x with an equivalent expression. Now, which one you remember, it's entirely up to you. If you can skip ahead one step from what I'm going to do, that's great. But the one that sticks in my head for cosine 2x, if you can remember more, that's great. But the one that I remember, more than any, is that cos 2x is the same as cos squared of x minus sine squared x. So I'm going to just replace that with what it is in terms of cosines and sines squared. And in the same way, sine 2x, I can use double angle formula again as well. Sine 2x is one of the same as 2 sine x cos x. So I'm just going to change that in a similar way. Write it as 2 sine x cos x. And again, that's multiplied at the end by a sine x. Now I tend to remember that sine squared is the same as 1 minus cos squared. So this here is the same as cos squared minus 1 minus cos squared. So minus minus cos squared gives 2 cos squareds. And then because sine squared is 1 minus cos squared, I still get a minus 1. Now, if you can remember this straight away, this step here you can sort of skip. If you know that cos 2x is 2 cos squared x minus 1 straight away, that saves you some time. Again, I'm going to have to times this by cos x on the outside still. And over here, 2 lots of sine x becomes 2 sine squared x cos x. The next step, I can now expand this out. So 2 cos squared x times another cos squared gives 2 cos cubed x. Minus 1 times cos x is just minus 1 cos x. But then sine squared, I can replace with 1 minus cos squared, because that is what sine squared, of course, actually is. So again, just another substitution for what sine squared is in terms of a cos squared, and almost done. So now I've got 2 cos cubed x minus cos x. Over here, I'm going to get minus 2 times 1, so minus 2 times cos x, so a minus another 2 cosines. Then minus 2 times minus cos squared gives positive 2 cos squared, times another cos gives positive 2 cos cubed x. Final step, piece all this together. 2 cos cubed plus another 2 cos cubed gives 4 cos cubed x minus cos minus another 2 coses is minus 3 cosine x. That's all in terms of powers of cosine, so I've answered the question, so we can stop there. So that's our expression in terms of just purely powers of cosines. B part 1 is a different sort of flavour. This time we're looking at proving an identity. So this time we've got cos over 1 plus sine plus 1 plus sine over cos. We need to prove it's one and the same as 2 sec x. So let's try this. By the way, when proving identities, it's often easier and quicker to do them with just letting C be cosine and S be sines. So I'm going to show you how you can do this now, in fact, because it's worth showing. So over here, let's C be cos x and S stand for sine x. Then what we have is cosine over 1 plus sine and plus 1 plus sine over cosine. So what we can do here is we can get a common denominator. So if I multiply top and bottom of the first fraction by c, and the other fraction if I multiply top and bottom by 1 plus sine, I'll get this as our next step. The first fraction will become c multiplied by c, which is c squared. Then the bottom becomes cosine multiplied by 1 plus sine. Then the other one is going to become 1 plus sine all squared. All over again the same common denominator now with cos brackets 1 plus sine. Because we now have a common denominator, we can of course combine these two fractions into one. Just merge the numerators essentially. So we'll now have cos squared on the top of the first fraction, of course, so put this in, and then what we'll do is expand out 1 plus sine all squared. This will give us 1 plus obviously 2 lots of sine plus sine squared. All of that's still over cos 1 plus sine. But at this step, we need to recall, ideally, what cos squared plus sine squared actually is. Cos squared plus sine squared equals 1, so we can replace this with 1. So that gives us 1, which is cos squared plus sine squared, plus another 1, which is 2, plus of course the 2 sines, all over cosine 1 plus sine. This can be factorized, of course. So 2 plus 2 sine is 2 lots of 1 plus sine, all over cosine 1 plus sine. Now we see that top and bottom will cancel. So we get 2 over c. Then just defining what c actually was. C was obviously cos x. So 2 over cos x is the same as 2 sec x as required. And so we're done. Well done for B part 1, at any rate. B part 2, we now have to essentially solve this equation using what we've got from before. So we're not going to try and solve this horrible mess, because we actually know that all this is the same as 2 sec x. So we're going to solve 2 sec x equals 4 instead, essentially because that's the much easier form to take. So this equals 4 is the same as saying 2 sec x equals 4. So that's our starting point. 2 sec x equals 4. Quite obviously, I think it's fair to say we could just divide both sides by 2. So in other words, sec x must be 2. But because sec is 1 over cosine, we can reciprocate both sides. So reciprocal of sec is cos, reciprocal of 2 is 1/2. So the solution we're after is where is cosine of x equal to 1/2. At this step you can use your calculator if you really want to. In fact, I would recommend you do so, because memories are fallible, but this is one of these exact trig ratios. So for this one, if we do cosine minus 1 to get the principal value, so therefore principal value is cos minus 1 of 1/2, and you should find that gives you pi over 3. However, we're solving it in between 0 and 2 pi. So actually pi over 3 isn't necessarily going to be our only solution. So if I just section off part 1 from this so it doesn't get too messy, that should do. So depending how you solve trig equations, my preference is to use a cast diagram. And of course we've got one solution, pi over 3. So if I just do a crisscross like so, label the quadrants cast for cosine, all, sine and tangent. I'm wanting obviously cosine to be positive 1/2. So in which quadrants are we looking at? It's A here and the cosine quadrant. So we have pi over 3 first, which is that one. So all of these acute angles in between the x-axis and these diagonal lines will be equal to pi over 3. So the first solution, pi over 3, we've got. The next one would be in the cosine quadrant, but because we want positive values only, we need to go all the way around from here. So it's all the way around like so, almost a full circle, almost 2 pi. So this one here is 2 pi minus pi by pi over 3, which is 5 pi over 3. So therefore, x equals pi over 3 or 5 pi over 3. Let's have a look at warm-up question 2 next. Warm-up question 2, and this is about implicit differentiation. So we have a curve with equation 3x² minus y² plus xy equals 4. Points P and Q lie on the curve. The gradient of a tangent to the curve is 8/3 at P and at Q. For part A, we have to use implicit differentiation to show that y minus 2x equals 0 at P and Q. So, differentiate each piece with respect to x. So 3x², differentiate that, it just becomes 6x. Differentiating y², I always think of it as imagining the y as an x. If that were minus x², that would differentiate to just minus 2x. Because it's y², that differentiates to minus 2y, and just then stick a dy by dx at the end of it. I do explain why this strange rule comes from in the actual section on differentiation. I'm not going to go into that here. I'm just going to compute and show what the solution is essentially. This one here, differentiating x, y, we need to use a product rule. So I'm going to hold x constant, differentiate y, which gives me x dy by dx. Now I'm going to hold y constant and differentiate x. Differentiate x with respect to x just gives 1, leaving me with just y. I now need to differentiate the other side. Differentiate a constant, of course, gives 0. I have dy by dx twice, so I can factorise out dy by dx. So dy by dx, I've got x there and minus 2y over there, plus 6x plus y equals 0. If I now rearrange, dy by dx, x minus 2y must equal minus 6x minus y by just subtracting 6x and subtracting y from both sides. I can now divide by x minus 2y. So that gives us that dy by dx must be minus 6x minus y all over x minus 2y. And dy by dx, of course, tells us the value of the gradient of a tangent to any point of a curve. But what it tells us here is the gradient of a tangent to the curve is 8/3 of the points we're interested in, P and Q. So I can set dy by dx to be equal to 8/3 and then get an expression for y in terms of x and hopefully arrive at this result. So the next step, I'm just going to say dy by dx is 8/3 at the points we're interested in. So 8/3 must equal minus 6x minus y all over x minus 2y. I can now solve this in a variety of ways. Use your personal preference if you wish. My personal preference is cross multiplication. So 8 times x minus 2y, and then 3 times minus 6 minus y. So 8 times x minus 2y gives 8x minus 16y. 3 times minus 6x is minus 18x. 3 times minus y is minus 3y. I can now add 16y to both sides to get the y's together. Or in fact what I could do, change of heart actually, just noticed I want one side equal to 0, so let's go for that. Let's get the y's positive and the x's negative. So yeah, if I add 3y, so 16y to both sides, yeah, that was right. And actually what I'm going to do, I'm going to subtract 8x from both sides too. So add 16y and subtract 8x. I was going to get y in terms of x, then rearrange, but we can do it in one go. So this side obviously becomes 0 because I've taken away 8x and added 16y. Over here, minus 3y plus 16y will give 13y. And then minus 18x minus another 8 gives minus 26x. We can now see, if I divide both sides by 13, we will get the required result. So therefore, y minus 2x does indeed equal 0 as required. For part B, we now need to find the coordinates of P and Q. So because we know that y minus 2x equals 0, for part B, we can rearrange that to get y in terms of x. We can say sub y equals 2x into the first equation. In other words, one that was given to us, this one. So all I'm going to do here is just replace each instance of y with 2x. Whoops, that was a mistake. So let's see what happens there. That's going to give us 3x squared minus y squared, which we're now going to write as 2x squared, plus x times y, which we're going to replace with 2x, equals 4. So that gives us 3x squared. This becomes minus 4x squared. X times 2x is 2x squared equals 4. This simplifies to be just 1x squared overall. So x squared equals 4. So therefore, quite clearly, square root both sides, but consider minus and positive root. X is minus 2 or 2. What on earth is that arrow? That's the worst arrow I've ever done. So if x was minus 2, and we know that essentially from here, just rearranging y is double x, I can just double both values to get the corresponding value for y. So when x is minus 2, y would be minus 4, or if x were 2, y would be double 2, which is 4. Just be very careful to answer the question as it's been asked. This looks absolutely fine for full marks, but the question does say specifically the coordinates. So therefore, in any order, P and Q are the points minus 2, minus 4, oops, minus 4, write what I say, and also 2, 4. So we've proven it perfectly, pretty much. So we've done the warm-ups. After the warm-up comes the main part of the lesson, which I'll try and explain as clear as I can. So, using summations, summation notation for integrals. So what does this mean? Integration is a limit of a sum. So, it is possible to approximate the area under a curve as the sum of the areas of a number of thin rectangular strips, each of width delta x. As these strips become thinner and thinner, the approximation becomes more and more accurate, and we can use limit notation to formalize the idea of a definite integral as the limit of a sum of the areas of these rectangular strips, which gives rise to this general result. The limit as delta x approaches 0, as the width becomes narrower and narrower towards 0, summing them up between x being a and x being b, the areas of those strips, which is their widths, multiplied by their heights, in other words, this is like y times the x distance, that actually tends to be the exact area if we were to integrate, which is the same as the integral in between b and a. So the book doesn't actually go into proving when and why this works, which is fine, because if it did, it would be quite an arduous process. Which is why there's no integration from first principles, essentially. So to explain why not, let's just think about this. Because in year 12, we saw that many functions can be differentiated from first principles, and this is a specific element of year 12 portion of the course, differentiation from first principles. For example, differentiating sine x, differentiating cosine x, differentiating powers of x. However, an A-level course doesn't include integration from first principles. Although it could theoretically include integration from first principles, it would be really narrow in its scope, and non-trivial questions on it would feel really awkward. If you don't take my word for it, I'll show you in a moment where you can look to see an example of one. It's so awkward and difficult, in fact, it took until the 19th century, Victorian era, in terms of, if you're British, for integrals to rigorously be defined and robustly proven to link to areas under curves for all continuous functions. So it's one thing trying to do this for y equals x squared or y equals x cubed, but to prove clearly and watertightly that if a curve is integrated between 2 points, that's one and the same as this limit sum, that's actually very, very tricky indeed. The fact these breakthroughs only came to light about 150 years or maybe slightly later after Isaac Newton's pioneering work on calculus, it proves the difficulty of truly proving it from first principles. Again, if you don't believe me, or if you're still interested, let's imagine trying to do it for y equals x cubed. Proving that the area from first principles between x equals a, x equals b, and y equals x cubed is the same as the integral is very long-winded, but it can be shown. This is entirely optional, so please treat this as this is optional. If you want to see how it might look if it were included, I've included a link in the video or on your notes. There's a QR code that takes you through how integration from first principles may look if it had been included on the A level. That clip, by the way, is looking at the particular example of integrating from first principles y equals x cubed in between a and b. It's not for the faint-hearted, and as I say, don't worry, you don't need to know it, but if you are interested in understanding in a slightly deeper way why integration works and what's actually going on behind the scenes of it, this might be of interest to you. I say maybe. So that's there purely optionally. What isn't optional, what is on the syllabus and needs to be learned, is the following. Essentially, all you need to know really, the bare bones is, if you ever see a question like this, essentially it's like the delta x you just replaced with a d and the sigma replaced with the integral sign. So this and that are one and the same. And so you just change this into that and then just treat it as though that step never happened. It's a very tokenistic part of the course, this. So let's have a look at an example. This is adapted, taken from a shadow paper. So worked example 1. The diagram shows below a sketch of a curve with equation y equals mod of root x. So essentially it's just the first quadrant, the positive square root of x. If the point P, defined parametrically as just x and y, lies on the curve somewhere here. There we go. The rectangle, shown shaded, has height y and width delta x. And it says to evaluate the limit as delta x approaches 0, the sum of all these strips in between x being 4 and x being 9. So all we need to do here is to realise we can replace that with the integral and replace that with dx. So the answer to this is actually surprisingly simple. So the limit as delta x approaches 0 of the summation from x being 4 up to x being 9 of mod root x delta x, this is one and the same as the integral from 4 up to 9 of mod x dx. But we can go one further. Square root of x we can just say is x to the half. So I'm just going to replace that with x to the half. You can leave your mod signs in if you really want to. So of course when we integrate functions algebraically, we just need to add 1 to this power of x. So 1/2 plus 1 gives 3/2. So it's going to become x to the 3/2. And then of course we divide by the new power. So dividing by 3 over 2 is the same as multiplying by 2 over 3. So integrating, putting the limits in. So the higher limit on x is 9. That's going to give us 2/3 of basically what the square root of 9 is. I'll put it in fully. Now we could do this on a calculator, but just for a bit of fun, I'm not sure if fun is the right word, I'm going to do it without a calculator, just going back to laws of indices. So the lower limit is 4 to the 3 over 2. So laws of indices, the bottom number means the root, the top number is a power. So I can square root 9, then do it cubed. Square root 9 is 3, 3 cubed is 27. So I've got 2/3 of 27 minus 2/3 of the square root of 4, then cubed. Square root of 4 is 2, then 2 cubed is 8. So 2/3 of 27, well 1/3 is 9, 2/3 is going to be 18, so I've got 18 there, and then 2/3 of 8, well can't really do that, I'm just going to have to leave that as 2 times 8, which is 16, all over 3. 18 is 54/3, so 54/3 minus 16/3 gives 38 over 3. Of course, that isn't wise. I just thought I'd do that just because these are nice numbers, as it were. However, what we need to do is see if we can do this on a calculator. I'm going to show you how. So, the new version of Classways I'm not a big fan of, but there is an equivalent function. On this one, it has an integration symbol. So literally just type it in. High limit was 9, lower limit was 4, and then what we had was root x. And it actually said mod of root x, didn't it, here? So if you want to, I can press, is it shift? Where's the mod symbol? Oh, abs. ABS on this one. So shift ABS, then square root symbol, which is going blind, shift, and just type in, oh, that's the third root. So what I'm looking at over here is I'll just type the square root, why not? So square root of x in between these limits, and you do get 38 over 3. So this is a really powerful checking tool. The calculator is really good in this regard. 38 over 3, which is what we got there. So over to you to just practice this relatively simply explained concept. It's presented very simply. We don't go into depth and actually use this idea beyond just switching the delta x for a d and replacing the sigma with integral notation. So there's only a few questions to try, hence try the whole exercise. It's 11L on page 330 of your Year 13 Blue Book. Try these. If you get stuck, let me know. I don't suspect you will, and keep plodding away. Integration is the biggest chapter and arguably perhaps the most important, so practice the questions long and hard. And if you run out of practice, the mixed exercise at the end of this chapter has lots of really good, fairly brutal questions. In the best way, I mean that, because the actual A level can be hard indeed. So I would suggest to keep picking away maybe a couple every few days and try and finish as many of the integration questions in the mixed exercise as you can before you actually do your final exam. Hope that's been useful, maybe interesting, but I'm not sure. I hope so. Thank you again for tuning in, and I'll see you all soon.